talk this morning. I'd like to welcome Ilya Goldsheid from Queen Mary, who will be speaking about recurrent random walks in random and quasi-periodic environments on a strip.
Okay. So thank you for asking me to give this talk, giving me the opportunity to talk. I don't know what. But, right, it will be a serious deviation from our general topic. I will be talking about random walks. The interesting fact is that the equations there, that arise there, they are sometimes very similar to what we look at here, Schrödinger equations, just that there is no spectral parameter. The spectral parameter is 0. And and of course, everything is very different in many ways. First of all, what is the model I'm going to consider? I'm going to consider the extension of the following model. You have a particle here at point n, and it is allowed to jump just one step to the right or one step to the left. So this is a classical one-dimensional random walk. The non-classical moment here is that the probability is Pn and Qn. Pn plus Qn is equal to 1, so no other options. And Pn are random. Pn IID random variables. Independent, identically distributed random variables. And this model was introduced essentially, well, in 1967. But the first serious result was by Solomon and then who was a student, I understand, of one of these people, Kesten, probably from Kozlov, Spitzer. And he was a student of Spitzer, I understand, who proved the following thing. And this is what he showed Solomon in 1975. And immediately his paper was followed by a paper by Kesten, Kozlov, and Spitzer, which went much further than Solomon went. But I will not be talking today about that. I will be talking about something. I will explain what I mean. But first of all, what did he prove? He said the following, that in order for the random walk to be, well, let's consider the following quantity. Lambda, by definition, will be the expectation of the log of Q divided by P, where Q and P have the same distribution as any of these Pn. And he proved the following fact. Lambda is equal to 0 if and only if the random walk is recurrent. Which means the following, that if a particle starts from here, it will go back and forth, reach every point on the line, and return to 0 infinitely many times as time passes by. Lambda less or greater than 0 if and only if the coordinate of the walk tends xt tends to plus minus infinity accordingly with these signs as t tends to infinity. Here there is no limit. There is upper limit is plus infinity, lower limit is minus infinity. But here,
what do you mean t? Is a particle spend some time at n side?
xt xt is the coordinate. You shall need it. T is time. Yes, yes, yes. Sorry, I misunderstood. Coordinate of
N before and now it's t.
n is a point on a lattice.
Okay.
And coordinate of the particle at time t, integer. Z plus. Oh, Z. Yeah, Z plus. Well, by which I mean zeros included. You never get it. Okay. Forget it. So this is a very classical thing. Now, there were many results since then, and this paper, it generated a subfield in probability, which is called random walks in random environment. Many papers, hundreds maybe. And so these two papers started all of that. I have to mention also the result, a result by Sinai in 1982. Sinai showed the following, that if lambda is equal to 0, then xt is over the log t squared. More precisely, if you divide xt by log t squared, it will converge in some weak sense. Now again, well, Sinai got, well, this thing got a name. He gave a name to the so-called Sinai diffusion as a result of this paper. It's a short paper. And there, in this paper, he asked the following question: what happens if the walk is slightly more complicated than that? What if it is allowed to jump not one step to the right and one step to the left, but several steps to the right and several steps to the left? In other words, it is characterized by P, by the probabilities P of nk. K, say, between m and minus m. Probabilities of jumps, this is n plus k. This is the probability of jump from n to n plus k. If the particle is here, it jumps here with this probability. Again, these, in fact, this is a vector, right? And this is a sequence of IID vectors. And the methods used here, in the simplest case, are non-trivial, but they are based on the fact that these are the nearest neighbors only, jumps only to nearest neighbors. It is absolutely crucial there. They solve equations explicitly, get some serious expressions. Since I was able to analyze it, in the case when lambda is equal to 0, when lambda is not equal, all the cases when lambda is not equal to 0 were analyzed by Keston, Kozlov, and Spitzer. They were not able to do the case lambda equal to 0, so he finished off the job. And as I said, gave a name to a new thing, Sinai diffusion. Now, there were attempts to develop this thing, and there was a paper by Key in 1985, I believe, who explained what would be the analog of this thing in some cases of this definition of lambda, which is in this case is trivial, but if you have many of these probabilities, what it is not quite trivial. I will not explain his result because his method was a little bit, well, there were many attempts to develop it, his method, but they didn't lead anywhere. But at least he gave a criteria in some terms for recurrence. I will explain a criteria which was given later by Bolthausen and myself, and a very different one. But I have to mention this work because this was before we did it. But the technique is very different, and it is absolutely crucial to have this different technique. Now, I will look at another extension of this model. Namely, I will look at a strip. And the random walk will be allowed to jump from any points, and I will call it layer n, to any point in principle, to any point in the nearest layer or inside. I will not tell it right now. I mean, I will not explain how, but this model, this one, is a particular case of that one. There is a very simple geometric construction when you simply cut the line into pieces of length m, and you turn these pieces, you turn these pieces by 90 degrees, and then you get a strip. And this problem reduces to this one. So it is a particular case of this one. I will mention something about the results concerning this model, because it is interesting and non-trivial, but I will be talking about this model only. As I said, this is a particular case. Now, how is this model characterized? Now, we have many more parameters in principle. We have probabilities of jumping from point ni. You can jump to n plus 1 j. You can jump from ni to nj inside the layer. So this is I, and this is j. This is the first option. This is the second one. And you can, of course, jump from ni to n minus 1j. This is what I said before. Now, the corresponding probabilities I will denote by different letters. These will be P n of ij. Inside, I will call them Rn of ij, and these will be Qn of ij. Now,
there was no R in the original model, right?
there was no R in the original model. That is true. R in the original model is 0. But here, it is absolutely unnatural to believe that we cannot jump inside. And moreover, we can also return in principle. Why not? So, in the original model, nothing like that. Not here, by the way. Here you can return, in principle. Possible. Okay. So these are, in fact, 3 matrices. And they will play the most important role for what I'm going to say. We have 3 matrices, Pn, consisting of these guys, Qn, Rn. I usually write them in this order. In some sense, we can get rid of this part, but it doesn't help too much. Forget it. And I will consider them to be IID. And also there is another class of matrices. When Pn, Qn, Rn is some transformation p to the power n applied to p, q, r, where p, q, r is a function, are functions. P is a function on some metric space, let us say x, into the set of matrices, into matrices, m by m. Now, what are the conditions I want to impose on these Pn, Qn, Rn? First of all, from the definition, it follows immediately that Pn plus Qn plus Rn one is 1, where 1 is this vector, 1, 1. Stochasticity. The meaning of this is very elementary. It simply means that that the sum of the probabilities of the jump from one point of all possible jumps is equal to 1. The particle jumps somewhere or stays. And this is the meaning of that. Now, once I have these, I will now do something mysterious. I will introduce, in order to state the results, I will introduce some strange matrices. Psi n will belong to the set of stochastic matrices psi, stochastic m times m matrices. They are defined in not in a quite trivial way, but if you have psi n minus 1, then psi n is equal to, choose any psi n minus 1, is equal to 1 identity matrix minus Rn minus Qn psi n minus 1 to the power minus 1 times Pn. I start with any matrix psi A. A will tend to minus infinity. And then under certain regularity conditions, let us, for simplicity only,
The difference between A and M.
I will explain in a second, but I have to mention the conditions first, which I always forget. There are some regularity conditions. For simplicity only, what I will say now is far too strong. But we don't need that much. But for simplicity, let us suppose that all these elements are simply larger than some small number epsilon larger than 0.
These are transition probabilities, right?
Sorry?
Transition probability is positive.
Yes, transition probabilities are all positive. It's not a very good condition. But just for the purpose of the talk, all what I will say is valid under much more general conditions. But to explain them will take too much time. Now, what I am doing here is the following: that when A tends to minus infinity, I can define psi n for n greater than or equal than A. If I choose a sequence psi A in arbitrary way, then limit of psi n as A tends to minus infinity, I will call zeta n. And it exists and is independent of the choice of psi A, arbitrary sequence, which tends to minus infinity. For every such sequence, for every psi A, I can do that. So what I am doing is the following. This is A, right? This is n. N is fixed. And then I take a psi A, I define all these matrices up to psi n according to this formula, A plus 1, and so on until psi n. And then I look at the limit. And this limit is always there. It is a deterministic fact. It is not random. If I have these conditions, and as I said, much milder conditions too, then this can always be done. And these matrices are stochastic. It's very easy to see, a very simple exercise, that if this is stochastic, then also this is stochastic.
So it is not clear to consider limit of Cn when what goes to infinity, A goes to infinity.
A goes to infinity. And as I said, this limit does not depend. Of course, obviously, if I choose different psi A, before the limit, they will be different. But the limit will not depend on it. They will be. So it's canonically defined in a sense. Now, let us now forget it. So we always can define it. But the remarkable fact is that if there is another way to say approximately the same thing, that if these matrices are Pn, Qn, Rn is an independent sequence of matrices, then psi n is a Markov chain. It's a particular case of what I said. Is a Markov chain on the set of matrices. It's a compact set. There is always an invariant measure. It is concentrated, this invariant measure, on these matrices θn. Just a lot of what we have done, and I am now talking about my work with Boltzhausen, which was published in 2000. This part is applying to very general, can be applied to very general stationary sequences, Pn, Qn, Rn. But in the case of independent matrices, this is just a Markov chain, and what I said means the following, that there is a unique invariant measure for this Markov chain, mu of d psi. Now, once I have these matrices, I can define An, which by definition is 1 minus Rn minus Qn zeta n to the power minus 1 times Qn. So the difference is between this one and this one is that, first of all, I take already the sequence zeta n, which I obtained, but instead of Pn, I have a Qn here. And now what is lambda, finally? So there are different ways to define what is lambda. One very non-constructive way, but is the following, but it is a shorter one. Lambda is the limit as n tends to infinity of the log of the norm an minus 1, a1. This limit exists with probability 1. This is simply a, because, well, by the way, this is, of course, a stationary sequence of matrices. In fact, they are, if P and Q and Rn are independent, this is a sequence of, yeah, no, sorry, irrelevant. Then this lambda can be computed in a different way. It can be computed as an integral of the log of the norm of a x d mu of psi x and dp. I am only writing it, I will not be explaining this too much, but I'm only writing it to tell that in principle, at least for the independent case, this is a computable quantity. If you want to use, well, it's very rare that you can, well, I actually don't know such cases, non-trivial cases, when you can compute the corresponding invariant measures explicitly, but of course, it is not, it is possible to do on a computer in principle. Now, again, we have the following situation. I can now say what it means. Lambda is equal to 0, recurrence, lambda less than or equal to 0, xt, the coordinate of the walk, the horizontal coordinate of the walk, tends to plus minus infinity, exactly as it was before. All this construction, which doesn't seem to be very simple, of course simplifies if the width of the strip is equal to 1. Because in this case, you will have exactly the previous model, and the matrices psi n, 1 by 1 matrices psi n are trivial. They all are just one number, 1. They do not exist there in a non-trivial form. And that is why nobody saw them before when one looked at this case. So this is not something you see there.
So lambda does not depend on R in this case?
Lambda depends on R because it is R is here.
So what is the formula for lambda in the 1 by 1 case?
Oh, but 1 by 1 case, lambda is there.
No, if R is non-zero.
No, if R, it will still be the same thing.
So it does not depend on R.
Well, in a sense, still will be the same thing if R is non-zero, yes. Will not depend, in a sense. Well, R influences P and Q. Right. Okay. Now, there was a lot of development of all of that. It is so. What I explained now is our first work with Bolthausen, where we proved this criteria, and we wrote another paper published in 2008, where we proved that the analog of Sinai's result. So we went in a different order. We first solved the problem which was considered to be more difficult. We went for it, and we proved that log of xt will be of order log t squared. Also for this model, if lambda equals to 0, but under certain additional conditions. And this is what I was going to talk about. So this was an introduction in a sense. What are the conditions? The conditions there are as follows. If so, it is not always true that the random walk will exhibit the Sinai behavior if lambda is equal to 0. This is a necessary condition for random walk to maybe have the Sinai behavior, but it is not enough. Now, it turns out that here some algebra comes into play. That if, in order to have the Sinai behavior, you need the following thing. You see, I have these matrices A. I'll call if PQR is from the support of the distribution of Pn, Qn, Rn. The distribution doesn't depend on n, of course. Then define psi as the solution of this equation. 1 minus p 1 minus r minus q to the power minus 1 times p psi. So I want to look at the fixed point of this equation. It always exists. It is unique. It is what I am saying is a theorem or lemma, whatever you call it. And obviously the solution is an algebraic function of p and q. It depends on p and q. It's an algebraic function. Now A will be the same thing, 1 minus r minus q psi to the power minus 1 times q. And it turns out
You choose a stochastic solution?
yeah, always stochastic. I'm not talking about any. Whenever psi is there, it is stochastic.
The statement is that in this algebraic equation has a kind of stochastic one stochastic.
There is one unique solution to this equation, which is stochastic. Yeah, that's true. Always. And I can look at this matrix. And I'm now in the case when lambda is equal to 0. I simply want to explain the algebraic condition. So we proved that for there to be the Sinai behavior, one has to have the following property of these matrices. Among them, there should be matrices which have eigenvalues which are larger than 1 or smaller than 1. Not all of them equal to 1. So the condition is as follows, that the support of Pn, Qn Rn does not belong to the set PQR such that determinant of A minus I is equal to 0. This is an algebraic condition. This is what we have shown. Now, it is not very constructive because you don't, it's not very easy to control. However, it is equivalent to a much simpler it is equivalent to a much simpler condition. Oh, at least if we have, as I said, P plus Q plus R is a stochastic matrix, I can always take a vector pi, a line, row vector, and write this equation. Because it is a stochastic matrix, it's simply the invariant measure of a Markov chain, elementary Markov chain, which is defined on these m points by means of this sum, with the transition probabilities defined by this sum of matrices. So this pi, I will call it pi PQR, always exists. Now this condition, algebraic condition, is equivalent to the following one. Set of PQR such that pi PQR times P minus Q times 1. 1 is the vector, so this is a number, is equal to 0. So this is an equivalent thing, and this is a theorem that they are equivalent. I will explain that if I have the time, but it is an interesting situation when this result, I don't know how to derive it directly, how to derive this from this directly, but probabilistic considerations allow to do that. Now, I have erased this picture where the walk is allowed to jump several steps to the right and several steps to the left. This condition for this model is equivalent to saying that k, p of nk, is equal to 0 for rho n and omega, k from minus m to n. You had these probabilities of jumps to the right and to the left, and this condition is equivalent to this one. Again, some derivation. Now, this condition means that xt, this is equivalent to saying that xt in this model is a martingale and hence it satisfies the central limit theory.
I'm sorry, I would listen.
Yes.
So this is the condition which is under which nice behavior does not hold.
Yes.
Okay.
Does
Exactly
it hold
that.
or does hold?
No, does not.
Does not.
Does not. As I said, for the Sinai behavior to hold, the support should have points which do not belong to this algebraic subvariety in the set of matrices. So what I am saying is the following, that in this set of matrices, P and Q, PQR, there is an algebraic surface. And if the support is not on this algebraic surface, then and lambda is equal to 0, then the Sinai behavior holds. If it is on the surface, then there is a question whether it holds or not. Now, at least in this model, for this model, already in the paper by Bolthausen and myself, we proved that this is the necessary and sufficient condition for non-Sinai behavior. And in this case, there is a central limit theorem behavior. So the situation is not very straightforward, namely because of that. Well, in one way is...
This is equivalent to lambda being 0.
Sorry?
In one-dimensional case, this seems to be equivalent to lambda being 0.
No, of course not.
It simply says P minus Q is 0, no?
No. Oh, you mean in the...
Right.
No, but here, no, I'm looking at the model when the jumps are of length m, which is larger than 1. But if it is just the nearest neighbors, then the only case is P equals Q equals 1/2. The only case, if m is 1, then this is simply Pn minus Qn is 0.
Right. But this precisely when lambda is 0. So
This, no. Pn minus Qn is 0. This means that the Pn equals to Qn is equal to 1/2. Yes, all of them. So this of course is the central limit behavior, but this is the only case, and it's not interesting. I mean, it is what we explain to our students usually, this case. But in general, this is a necessary and sufficient condition for non-Sinai behavior, and the behavior is the central limit theorem described by the central limit theorem. So the question which I wanted to, the purpose of this, the newest result which I wanted to discuss is the following thing. It addresses the following problem. When the support is on this manifold, what happens then? In order to achieve full classification, you have to consider also that. So in most of the cases, we have, if lambda is 0, then in most of the cases, we have the Sinai behavior, because once one point of the support is not there, everything is fine. But if the support is on this manifold, it does not mean still that we have non-Sinai behavior, or we have the central limit behavior, or something else. Now, this is what Dima Dolgopyat and we did recently, and there is now, in a sense, a complete classification of these walks. Namely, I will explain a little more. It turns out that only two possibilities are there. Either there is the Sinai behavior or the central limit theorem holds. Now, this is quite a constructive condition. It's very easy to check. If you know the support of the measure, you can easily compute this and see whether this condition is satisfied by all the points in the support. Now, unfortunately, when you have a strip even of width 2, it is not so simple. We actually have the classification for the case 2, but I will not present it. It is messy. There are 4 different cases, long formulae. It is there, you simply believe me. But in more general terms, I will explain how these conditions, what these conditions are for non-Sinai behavior. So the first one I did explain already. We have all matrices of the support. They have to belong to this manifold, which I will write now in this form. This is the first equation. Now, the meaning of this is the following. I will explain the meaning of what I wrote there. You take, it's a matter, sometimes in differential equations, they call it method of frozen coefficients. You take the environment and you consider, you fix PQR, 3 matrices. And then you consider environment which has all these matrices, all 3 matrices everywhere. So it's a constant in N. It does not depend on N. Of course, along the line, well, we have these 3 matrices there. But the matrices do not depend on N. And of course, this is not a very difficult problem to solve. It is you can ask a good student to explain in what case a random walk will be recurrent and in what case it will be transient. But of course, in this environment, in a constant environment, you always have, this is exactly the condition for a random walk to be recurrent. And it is equivalent to the condition that the matrix A for this PQR has the top eigenvalue of the matrix A is equal to 1. It is equivalent to it. Now, it turns out that in order to have this non-finite behavior, we have to do the following thing. We have to take any periodic environment. Let me call it omega so that I don't write all the time 3 letters. And we have to take omega 1, omega n, and then construct a periodic environment, omega n, and then again omega 1, and so on. And it turns out that the random walk will not behave according to scenario, will have the central limit behavior if and only if it is recurrent for every such periodic environment constructed from matrices belonging to the support of the measure. I'm talking about the IID case. You can write explicit equations for that. It is a sequence omega 1, omega n, such that its invariant measure, pi 1 times q1, 1 minus pi n pn, one of pn is 0. So it is again an algebraic equation. I did not explain what is pi 1, pi n. I can explain it. What I want to say is that, in fact, there is an infinite system of algebraic equations which have to be satisfied. However, here, algebra plays a very important role. This infinite system of equations is equivalent to a finite system of equations at some point. But we unfortunately do not know how to constructively say which point n it is, except of the case when there are 2 by 2 matrices where we can classify everything. But in general, we do not know how to say it. But at some point, all these equations will, adding new equations will not give new restrictions. And so it is, in fact, a finite system of equations that will have to be satisfied. However, this first equation, it is in a sense canonical. It does not depend on the support of the measure. But these, they will, because we take these matrices from the support, and in order to have these equations on the matrices PQR, we have to consider omega 2 and so on, omega n, as parameters. So every next equation depends on a number of parameters. And we consider it as an equation on omega 1. And this is how it works. I would be happy to explain it in a better way, but I think I have to, I don't think I have a chance because it is really involved. I think that is it. So there is, the final thing is that there is a complete classification of these walks in some quasi-periodic environments on a torus. If these matrices are, say, Pn is P of some P function of t to the power n omega, or as you say, P of n
Omega plus theta.
yes, and omega plus theta. Well, and gamma plus theta, whatever. On a torus, there is a full classification. Also a problem which was dealt with a number of people, with some people, but never solved. In this case, remarkably, the random walk is always, never exhibits the does never exhibit the Sinai behavior. It is always the central limit theorem behavior.
Absolutely always. Absolutely always.
Absolutely always for sufficiently, well, let me be more precise, for sufficiently smooth P. Smooth, not analytic, just smooth. If P is sufficiently smooth, non-trivial, then there is always the Sinai behavior. So we can have all these cases, whether lambda is 0, then it is one reason. If lambda is not 0, it is another reason. This is not the case here. I didn't say anything about these cases. It's a lot of work there, and it was done. But this is a particular situation, a very peculiar thing. Anyway, but so there are two cases which are completely classified: IID environments and environments of this sort. Well, of course, Pn, Qn, Rn are similar. Okay, thank you very much.
Questions?
What happens at long range hopping terms? If you have, in one dimension, if you have long range hoppings?
Long range, you mean infinite range or?
Infinite.
Nobody knows. Nobody knows. Widely open. Everybody is welcome to try.
Have any other environments been considered? Have any other environments been considered, other ergodic environments?
Except of, not really, no. The problem is so non-trivial. Well, in the case of independent environments, probably the most interesting one, and it is completely non-trivial. Well, there are some results for the case when this is not a linear shift on a torus of, for instance, a skew shift, result, but not in the case when lambda is equal to 0.
So what is the result of this question? Is it CNI behavior or CLT or something?
No, it's a CLT behavior. As I said, if you have if you have a uniquely ergodic dynamical system which generates these matrices Pn, Q, and Rn, then if lambda is not 0, then it's always the central limit theorem behavior. If lambda is 0, we don't know. Again, this is open. And here, you only know it for sufficiently smooth, for coefficients which are sufficiently smooth.
For skew shift, you don't know for lambda.
Sorry?
For skew shift and lambda equal to 0, you don't know.
If lambda is equal to 0, no. We don't know. No, nobody does.
Even in one dimension.
Even in one dimension. In one dimension, I proved it first for, yeah. Even in the nearest neighbor case. Not no.
And if you have a hyperbolic dynamics, like
Hyperbolic dynamics. We didn't look at it, but I'm sure that, with hyperbolic dynamics, I'm sure it is very close to the independent case, but there is no formal paper about that. We only looked at these two cases. I mean, this one is actually this one. After you have all these techniques, this one turns out to be very simple. After. Very important point. But then it turned out to be simple. The IID case, not simple at all. More complicated. Strangely enough. That's the situation.
Any other questions? Okay, well, let's thank the speaker again.